Okay, this doesn't seem to work. Oh, yes. Okay. I did a short test run on it, and I didn't have to do it then, but maybe a good idea for Windows 7 anyway. At least it doesn't crash. So, welcome to the session. Maybe these two guys over there on the table. These are the startings 1 and 3, and I always carry them around Firebird conferences because I think it's fair that they get to see some Firebird people. Okay, what is this session all about? Session is really a piece of cake. I'll try to make it as simple as possible. But to be honest, it's really about a piece of cake. What I'm really talking about is, I don't know if you notice, it's quite delicious. You can ask yourself, what is this? We'll see that just in a moment. So, short intro for this session, we'll make a very quick run through the basics of trees and databases. I must mention that this was a 2-hour session before, and now I only have 1 hour time, so I'll just talk twice as fast. We'll take a look at recursive store procedures. Very short, because I guess all of you have sometimes done something in store procedures. Has anybody of you ever written a recursive store procedure? Okay, so I won't have to tell too much about that. Nested sets, magic. Has anyone of you ever worked with nested sets? Okay. And then, of course, which is really the main part of the session, is about recursive CTEs. Who has used recursive CTEs? No? Oh, quite a few. Good, fine. And afterwards, if we still have time, we'll have to see that. I'll show some real examples of what you can do with recursive CTEs and stuff. Okay, just basic definition of some terms that we use throughout the session. You have a tree with a root, obviously, and then you have branches of the tree, which we call nodes in IT. And usually, unless it's multiple, they have roots. When I see those pointers, I'm always press across this doesn't look right on programmer. So let's make this a bit right on programmer. That's better. So, we have this basic structure in almost any tree that we work with. Just a definition of the root node is also known as the roots. There are no other node above it. All of them are big nodes, but the roots are really so special. So nodes can have either better or not charts on. And previously we have the leaf nodes, which is just determining so the nodes in the lower and have no other nodes beneath them. What you see here actually is two siblings. It's like a operating system doesn't have the same values. So not all these are the same level, but it depends on the ones that have the same parent or siblings. Okay, we can have different relations of nodes in trees. One very common relation is an owner or containing relation. And this is typically what you have, for example, in a file system. In a file system, you can have files in one directory, and they are only in this one directory. So they are really contained in the directory. So one node is really contained in its parent node. This basically means that when you delete a directory, you will delete all the nodes in it. And this is kind of different from the other type of trees that we are usually working with. So, like what we have in our recipe databases, you have recipes or sub-recipes, and you have building blocks of recipes that you can piece together to form a bigger recipe. And so you can have recipes referencing other recipes, sub-recipes. And one sub-recipe can actually be part of a lot of bigger recipes at the same time, which obviously means that if you delete a master recipe, you don't want to delete all the child recipes because they can be used in other trees. So it's not a, what do you want to say, referencing trees. And so you can have the references of one node that references another tree or a subnode in another tree. Different tree types. The common case is that you have homogeneous trees, which means that all nodes in the tree have the same type. This is already different in file systems because you have directories and files. There are all nodes in this tree, but they're quite different. In SQL, you would say that a homogeneous tree is the tree where all node data comes from the same table. And then you have what we call heterogeneous trees. So you can have different elements as nodes throughout the tree. And this means that all of those nodes have different data, or record types, or object types, or whatever. And in SQL, obviously, this would mean that the data actually inside those nodes is spread throughout various tables in your database. Now, what options do we have to store those table structures in a database? The most common one, I would guess, is to store a reference to the parent node in every child node. This is a kind of classic approach, and it allows one parent node to have practically a limited number of child nodes. But you also have the other way around, and this is quite common in search trees, private search trees, where you have one parent node, and inside the parent node you have the pointers to the left and right or back and right child nodes. This obviously means you have a limited number of children, which is okay with binary search trees because you only need 2 childs, and that's what they're really made for. Another way, and this is what I'm going to show with the recursive CTEs in the end, is to completely separate the node data from the structure of the tree, which basically means that you just store the tree nodes and the pointers in a tree table and store all the data from the nodes in various different data tables. This is the most flexible way you can get with trees because you can really put anything into that tree. But if you want to retrieve the tree data, you obviously need a lot of joins and subsets and stuff to put in the real data for the nodes into your result set. And it also allows for a heterogeneous tree, so you can really spread the data throughout various tables. Basic feature here is that you use the separated structure of the tree from its content. And that's quite important. And then we have one that looks a bit like the search tree thing here, but it's actually not. Because you can have entries, just like with this option, with this one. And this is a somewhat strange strategy because you don't store any references from one node to another, but you just store numbers that will give you a guideline on how to walk through the tree. And this is what nested sets do. So, what we need to get our tree back on the database is to present it to equal or sustain or threshold trees and whatever. We have basically 2 options. We can do the recursion on the client side, or we can do the server side. Client side recursion is what we usually do with the OEM based purposes because it's doing the recursion on the server side. We basically need to start with selecting the parent nodes or the root nodes. And from that node, we select the child nodes. And for each child node, you select and one node down, one select. And you can see that's one node selected to get the tree data. On the server side, we have basically 3 options. First is recursive store procedures, obviously. Another one is recursive count table expressions. And the main advantage here is that you get the entire tree data back with just one statement from the client to the server. You get all 3 in one node. And the third option is really not a recursive option because nested sets aren't recursed recursively, but they return recursive data. So this is not a recursion deal with the server side. So, the pros of having the recursion on the client side is obviously that as the client application programmer, you have complete control. You can do whatever you want. You can control how you use the tree. You can stop any time you proposal. Once you have a note that you're looking for request, you can just quit. And in the proposal, you can change the proposal, so you have complete control. And so this is why I like to compare with usually our single step mode. So it's like when you definitely 7, every time you do that, you can make your mind going further or stuff like that. Usually, this is not really the best option. Why? First, it's slow, and it's expensive. But it's expensive in terms of server resources, server time. The client side, we have seen you do a lot of things. Let's say you have part of the server, you know. So as well prepares, you can reduce it by using burn class queries, but still you have a lot of statements involved and a lot of round trips across the network. You have to go from everything out to already set up nodes, or network nodes, you have to go back to the server and do something like that to get the next level back. And what we can do is what we can with our recursion, the server side recursion can do, is that you get all the thing in just one block. One statement and you get the entire tree back. So, let's take a look at the stock rocks. As I've seen many of you have already covered that, so I'm pretty sure on that one. Obviously, stock rocks can call other stock rocks, including themselves, which is the principle of recursion of this thing. You can have that with a directory. You can go and stock rock that directly calls itself if it's running. And you can also do that too. You can write two procedures that call each other. So basically what you're doing is you start with selecting parent nodes. And for that on, you do a for select loop. And in that for select loop, you call this stop procedure that returns the nodes itself. And you get the principle, I think. But we have this database that has all the examples that are here. If I get time to show it here. And there's some examples of stock procedures in here, or recursive stock procedures, but also a lot of procedures. You know, if you use this session, remember here, that is again just going out and this database, and also the procedure. So, what are the good things about stock rocks? Because we've seen that this, on the server side, when this recursion is happening, you have pretty few round trips. You just call the procedure once and get all your tree data back. And they are very fast because they are pretty fast. So once you have a lot of procedures, one interpreter will that's less than 100% the server. That's part of the stuff. Because the precompile, they're pretty fast. And you have about the same flexibility as with client-side recursion, and that you can do lots of things with stock procedures. Plus, one last thing is you have complete access to all of these features. So you can write stock procedures that propose a tree and do something with the data, like pump it over to another table. Actually, you have quite some stock rocks in the database that's show how you insert a normal tree structure into a nested set, and how you operate nested set tree structures, and measures how updating which tree you want to go, because they build up the nested set data from a normal nested tree structure. So this is kind of nice to do all this kind of stuff, those stock rocks. They have a couple of products. First, they're pretty complex. Like when your client's programmer, you can only use the stock procedures that are in the database. Of course, you can write these stock procedures, but you have to write down. And if you just use the database, and somebody tells you, like, here, this is a recursive stock procedure, you can call it and use it. You can't really see what's going on inside. Of course, everybody has database tools, so you can do the source, but just on the client side, it's like one block that you can look into. You just select from the stock procedure and you can see what's going on inside. When you have a lot of those stock procedures calling each other, they can be hard to maintain. Actually, it can become quite a nightmare to maintain if you're doing too many of those. And you always must remember to grants and store procedures. So they're less intense when it comes to managing the okay, let's take this. Put it in set. And take the set. Then we nest set 1 into set 2. What do you get? You get this. So this is a review of our set theory, which tends to just take passively into these structures. So let's take a look at this one. This is really classical tree as a canvas. And when you picture this as nested sets, this is what it looks like. So 3 are complete. And it may look like it, but it's not like it. Okay. We'll just do some different views from those nested sets. It's still the same thing, just modeling it in one way. What you can do is, you can imagine when you propose this tree here, a nested set, you just go this route through the entire set. Now, whenever you cross the border from one node to another, you can label this border with a number. And so you have 10 borders to cross when you go through this entire set. Now, where you go is would be like that. And so here you have your numbers when you're entering and when you're leaving a node. So, what this gives as a nested set is this kind of tree to draw. And you see that all the nodes get numbers, which are called the left and right values in nested sets. And whatever you do is you just tell them which order you have to traverse the tree. So, for see this node, it has 1, so you have to find the next node that has a 2, and you have to find the next one that has a 3. When you don't find any more nodes that have a 4 on the left side, and this is the charcoal, and the 4 is here, so this is just really the order how you have to move in this tree. And that's really the whole trick about nested sets. Now let's take some of the basic principles. There's just a definition. You say that the nested set starts off with a left value of 1, and the left value is smaller than the right value for all the nodes in the tree. Next we have the observation that the left value of the upper nodes is always smaller than the left value of the lower nodes. And the same goes the other way around for the right value. So the right value of the lower nodes is always smaller than the right value of the upper nodes when you traverse back up the tree. And one funny thing is that you can actually calculate the number of child nodes just looking at those two numbers. It's a simple formula. It's like 7 times 2 is 5, minus 1 is 4. And that by half. Oh, I forgot about half here. Damn. So you have to divide it by 2, and then you get the number of child nodes. So imagine divided by 2. Oh, there you go. There it is. Oh, I was 1 line ahead. So actually what this is saying is that the lead nodes have the left and right values that are next to each other because it's the ones between just the values. And there you have the formula. Right hand value divided by 2. This looks pretty cool. It's really easy to store them in a database, but you need 2 fields. Because they have a parameter in something, you just have to run the left and right values. And as you can see, if you traverse the tree, you just have to traverse the nodes in the order of left. So that's really cheap in the database, because you just need to put it in next and nothing else. And you just get the entire screen with one selected right order. One of the real drawbacks in nested sets is that they're pretty costly to maintain if you have changes in the nodes. As an example, just take a look at an insert statement. So we want to insert one node beneath this field node here. And you see the numbering is quite easy. but you also see that not only this node is new, but you have to update this node and update this node. So you can change the number. This is kind of the best case example. It takes worse when you insert the nodes out to the left, because then there's a lot of other nodes that you have to update. And the worst case, it can be that not only one node needs to have to update all nodes in the entire structure. This is also part of what's in here, how it is in real life. Also same principle. It's that when you're using extensive sets, it's not enough to just insert one node. You have to update other nodes to reflect those non-coding changes throughout the nested set. So, what are the pros, really, of those nested sets? They are very good if you have static trees. We have trees where you know they have points, and it's likely to suddenly change. So you have a tree that's red very often, but maybe to suddenly, but that's exactly what we do as all the purposes. They're very fast. Actually, they're unpredictable in speed. You can't have any other structure or retreat as fast as a nested set, because you just have to get some or other fields in the ground. So that's what we do that with recursive CTEs, still possible, whatever else. And you can also use some trees. The sample database have one of the tables where you actually have a combination of a parent ID in each record and the LMR values. So you can use the method that suits you best. The only thing that you have to remember is that when you update a tree, like letting it over the parent ID, then you have to use a procedure to update the LMR values. But that's sort of because it's not procedures in the sample database that will do exactly like what you do that in order to just update the LMR values in the whiteboard. And anyway, it's all the start of nested sets is pretty well documented. You can find a lot of examples and examples in the world. Obviously, they have some drawbacks as well. One of the drawbacks is that updating routines is really expensive. Whenever you change something, you have a lot of updates. It's not really hard to do these updates because basically you insert each other out. Try out needs two new updates. So what you do is you shift all the other ones to ahead. So you don't really have to walk through the tree to update it. But you just move up the institutions and those at the right level. But still, it's work to do, and you have to do it unless you do it as a structure. One thing that's also a big cost is you have no direct link between parent and child nodes. So if you just have one node and that's 5 is left and it's 17 is right value, you have no way to tell what is the direct parent. It's going to be parent. Which is not really important. And I'm not really sure this is pro or wrong, but you have a predefined order of charts. The charts from left to right are numbered from left to right. So you can just say, I want to outline the number around, because then you have to be number of values. You can't define all which nodes are the same value, just by judging the right values. So that's been odd, but if you have a tree, classical example is like a discussion forum where you have one name forum and totally subforums, subforums. We have set up this thing once, and the forum is now likely to be changed. And you have to know what else we can do. And for this kind of use case, this is a very strong weapon. Okay. Let's head to the main part, which is recursive data expressions. I saw some hands go up questioning what with recursive CTEs. As all of you has worked with CTEs know. How data expressions is important. That's funny. Let's There is at least with CTEs. Maybe I'll just show this slide then anyway. Okay. Still to come, so let's just continue. Let's start with the downsides of the recursive CTEs. Obviously, when you use them for clients, the time is really understand the case structure. But he was also able to understand the case structure what others was offering. What you have is you don't have PSP clients, so it's just basically one statement that is sent to the server and gets executed, but you can't do what this stuff while doing and this is it sad, because I would make all the charcoals and forms. It's going to come in the future file versions, and I don't know questions about it, but maybe we know that, so I'll show you some slides where we see how this can work. The pros of CTEs are really just about the rest. We have server-side recursion, so we don't have to piece together a big tree on client side, and we have one single statement. Therefore, they're very fast, which is also due to the fact how they're implemented. We're going to be going into a little more detail on that. It's pretty clever how they're implemented. They are very flexible because you can just piece together whatever CTE, whatever tree you want from the client side and send it over. Therefore, they're also very transparent with the client, so you can fully control the tree proposal. And I think they have pretty elements in CTEs. Once you get the basic principle, it's quite easy to follow how the tree really works. As compared to the storehouse, I think one of the main advantages is you don't have to change the data to change the way you get feedback. You just send another statement to the server, but you don't need to recompile in the storehouse and stuff. And obviously, you need the runs to the fields that you're querying from, but you don't need runs to the storehouse procedures. But you can also use them in store procedures because it's basically just an extension to the select statement. So you can use wherever you can use the select statement in store procedure or trigger or wherever you can also use recursive CTEs. Okay, so let's look taking that normal CTEs first because I saw that not many of you yet worked them. Basically, it's that you just have an ordinary select statement here. But you don't select from the table, you define something like a view before the actual select statement with a width clause, and you give it an alias name, which is just an alias name like you have with the table alias, or alias, and you have just a normal select statement inside braces. And this is the preamble of the select. And after that, you have the select that queries this alias. Another thing you can do is you can use more than one CTE in such a select statement. So you can actually write one alias and input one select expression, and just separate it with a comma, and use another alias. Another select expression. And then you can do stuff like this. You can select from the first CTE and join that with the second CTE. Or use the second CTE in a web region or whatever you want to do. So you can combine them. And so you can really chain CTEs because what you can also do is in this CTE, you can select from this CTE. So you can really pull it out. And all of the same statement. But if you have a discover one node, actually, this taking is something that I use quite a lot because, to be quite honest, I'm also so good with tons of 5 tables to solve. And with Python, so I just sometimes I'm following anymore. And this is kind of easy. You can take a complex problem and we put it down into little pieces and put one piece in one CTE and another piece in another CTE, and then you can test those independently of each other. That is very easy. So it's actually also good to understand complex statements. Okay, let's look at recursive CTEs. Those are basically just the same as normal CTEs with one exception. So you can see that it's just like a queue. It's like a pair of queue. It's like when you just present the same statement. And the thing about recursive CTEs is that they can hyperiterate on themselves. So if you have one CTE and inside that CTE, if you join on the CTE, we will see that. So there's one thing that I want you to remember from this session is that you can actually completely traverse these structures with CTEs with a single select statement from the client, and that's very efficient. Okay. Let's take a look at how this works in SQL syntax. The key thing is here, if you want to do a recursive CTE, you have to tell the engine by using recursive. And then that's just like that with non-recursive CTEs. First, you start off with selecting root nodes data. And the magic thing here is the union all that comes after that. And you'll notice that we'll select the child data. You'll see in a minute that this select here is actually only executed once, only for the root nodes. And all the other stuff is done by this one here. The trick is, in the chart select, you join on the CTE alias, so you join this recursive CTE on itself on the parent condition. I always look at these brackets and I tend to write them there because I'm a better programmer, but you don't need to do it. Don't do it. And then obviously, so this entire thing is the preamble, that's the CTE definition, and afterwards you just go inside from the CTE. Practical example. Let's imagine we have a table where we want to store a file system. So we'll just declare our recursive CTE aliases file system tree. And first we select the root node. This is a pretty simple example. It's just an ID and the file name. And we'll switch over to SQL. I'll show you the example in real just in a moment. So the thing here is that you need one condition here that will return the root node. By the way, if you do this from the client side, you can also use a parameterized query and put a parameter here. But now just an example, it's just a static. 0. And then we have the union rule, and we do the chart select. So here's where you have the thing. So the file system tree is really where the parent node lies, and the link condition is that I have field ID master, the table, which points to the parent node, and you just take the join condition as that the ID of the master of the child must be the parent ID, which is actually coming from there. So this is what I call parent. So this is really what's happening here. It has a recursion. It's done by linking this here to this first second one. And then, of course, if you select from the file system tree. Since we're pretty good in time, I'll just switch over and show this in real. If I can find my to-do workbench, there it is. Okay. So this is basically the same example. Is that people? Let's just increase the font size so we can find it. And where is it? Oh. Oh, there. Okay. Oh, this should be enough. I don't think this was the right one. Okay. It's a bit stupid if you can't read it, so we'll just do something else. I'll just push down screen resolution. Oops. There. Too many open windows error. Okay. So I hope it's a little bit better now. You see, it's basically the same example as what we have in the slides. Maybe I should show you the table first. It's a very simple table where you just have basically each node has an ID. Each node has an ID of its master nodes, and then a file name. And you can forget about the IDs. They're not important for the example. It's just important that you have the link from the child nodes to the parent nodes. Actually, this is a pretty neat tree to address CTEs because it's constructed in such a way that it will show the problems that we have with memory. Because what you see here, I have this drive entry, and then I have a directory. And then I have another directory that actually this is the child of this one. So the tree is not in actual mode, it's upside down. And this is something that you should really do if you have testing recursive CTEs, because you get funny results, or you get results that you expect of their coincidence. So just do some mini ordering stuff to see the twist that works. Because if you just put in the data, the natural way that it should come out, and if you sort of recursive CTEs, you have a chance that the results are not correct, but it's just correct because the data was already in the correct order. So it's always a good idea to put some index in here to really check this. Okay, this is basically what we have on the slide. We select the ID file name, and then we do the join here by saying that the child's ID master field must be the ID of this here. And this is just the device of our recursive CTE. One thing I did here is I always like when these are indented, you can really see the structure. And there's a pretty simple trick to get that in the recursive CTE. You start off with an empty character field in the root select, and in the child select, you just extend that with a couple of lines. And then in your file select, you can just use this indent fields, which will have as many blanks as the levels of the tree is deep, and just concatenate that with the name. And here you can see the result. So you start in the root, then you have the drive, you have the main directory, and then you have on that level 2 directories, and each has some entries in it. And as I said before, this is kind of a feature because you see that memory, and it's not really working on that. We like all this from A to Z. Oh, there we go. get a little bit more technical. So what you basically send is this recursive CTE definition. And what the server does with this is actually prepare and execute phase. In the preparation phase, the most important thing that happens is that the child select, this one here, it gets transformed. So this join condition is never executed as a join. What the engine does is it replaces this join with a record of parameters. So what you get then is select child, where child parameters is ID. And then, of course, the statements get prepared. It's actually, as I said, two statements. One for the anchor select, and the second statement for the recursive traversal. When we get back when the engine starts processing the CTE, first the anchor query is executed. So that's the parent select. And this is really executed only once. No matter how complex the tree is, there's one select that we node, and then the statement is like gone. It's not used anymore. Then with the ID that is found in the parent select, this is used as a parameter for the child select. So for each child node that is found, the node is returned to the client, and then the entire statement, this child side statement, is really pushed to the stack. It's probably not 100% right, but it's not how this works. So just a fact that you just need to be after this push, the same child select is actually executed again, but with the ID from the first child select. So it's really the same statement that's just being used. And if it finds any child there, then we get a call. And this is really the recursive call, which pushes the tree one level down and starts here again. And this goes down, one level down, down, at the bottom node of the tree. When the bottom node is reached, the recursive optimizer goes up one level. And then the result set from the first operation that was pushed to the stack here is popped from the stack, and it goes over the next node. And so this is really just a loop. So there are a combination of loop and a calling loop. And the thing about this is that the entire process is done with the child select. It's connected once, and then it's just reused, push parameters into it, reuse, push parameters, and so you have just one operation requires to execute this. This slide I wrote from last was meant to give it to me, but I couldn't have done it in a better way, so so you can see the output of the anchor select. As I said, one time this is executed, it goes to one more. And all the other stuff is actually from the same second select, from the same child select, but it's just set with different parameters. Here it is the first node, which is the here. And then we get the sequence. And then it goes back. Oh no, actually, it goes here. And then it goes there. And then on once. And what you get is this lovely, helpful recursive combo with just two statements. So, as I mentioned, this is the anchor select, and the rest is all the same child select. One thing we have with recursive CTEs is just what we saw here. It outputs the tree very nicely, but probably not in the way, in the order that you expect. And this is, at the moment, this is completely way. This is just by using the tree, because you have to select the trees together. And the simplest method just to do this, or use all the bytecauses in everything that you do. So if you do select union or no select, you can't have more or less. It's just by using this kind of definition. So it would be nice nice if you could just go here. Oops. And just do something like, okay, let me order this by, this file name. I wonder if it executes at all. But anyway, you see, it doesn't work. It's still the same order. I actually would have expected to get really some kind of error message, but anyway, this order line is something we can do when it comes to CTEs. So, the thing is, you cannot control the output or the order of the output of this child select. Stupid. That's why I said it's good to have data that is in unnatural order, because if you put it in the right order, these charts are actually ordered because they are not at all. It's just coincidence. It's random how they come out. If you do it 4 times, if you get the same order 5 times, I mean that if you put in different data, it will still work. So, I have 4 solutions to this problem, and actually 2 of them really work, but not so well. The others do not. So I like it. The really one perfect way to do this is the sequence standard defines a force for especially when CTEs that says that first by and then hopefully comes water. Which means that we will down to the depth first. There's another variation that's called breadth first. This is where we go from the nodes. But the first is where the chart comes, and then goes through all the different chart comes first before it goes to the paper. And found in use case of that is standard defining. I guess in this case it's and then we just go that first line fine, and then all the charts are fine. And the good thing about it is that this will really order the chart select just the way we want it. It's actually just the same as doing the order by the chart select. It's just this means that the only data comes out of the select group in the right order on it, which is of course that we don't think have products. We have recursive implementation almost complete, but this is one thing that is still missing. So I can already tell you if you're looking at the CTEs, you can know this is important to have, because it's using a lot of Java already. Therefore, we have a stronger information, go to platform, rather than have them implement this. Okay, next thing I thought should maybe work. In Firebird, we have the window functions, and you have probably seen this in platform application. Window functions have one line, so we can't have an order by select when it's a window function with another line. And this might just work. There's 2 mistakes in there. The first mistake is the thinking mistake I made, and the second mistake is about the engine. The thinking mistake is that the window functions don't really order your result set. The standard is when you just use the window function, it seems to order your result set, but it's not in a reliable way. There's one algorithm that really makes this point. Imagine we do this. So it should order by our family. But you can have multiple window functions in the same select. So what if you do this one? Order by file name, and you do another one, order by ID. What will be the order of the chart records? It's completely. And this is why actually this order is also. The second thing is actually when you try to use this. I don't know if I can demonstrate it. It's probably better not to because it may put my my machine in an unworkable state, but I'll try it anyway. I got the Firebird tree here, And I made a very simple test table, which is basically just things perfectly with an ID, a parent ID, and a name. And it, screen resolution is really a problem here. It has just 3 records, and a parent and 2 charts, which I will be in the wrong order here. And what happens when you try to run this one? Back to the people here. So what I really tried was to use this window function and partition it by the ID and order by what I wanted to order by. Actually, when you execute it, oops. Oh, yeah. Oh, I changed the alias after I prepared the example. So I'll just quickly rewrite that. Oops. So you can see it's executing here. And it's executing for a pretty long time. And nothing happens. Another good news is it doesn't crash the engine. After a while, we get a technical message which basically says that you've reached the maximum recursion level. This is something that I changed. You have a maximum recursion depth of 1,024 levels. So you have a tree that's equal to 1,024 levels. You have this level. The engine has. Okay, so after a while, the server says, too many concurrent executions of the same request. Now this may sound like a strange error message. Let's just look at actually the translate. So it's the same select, which is pushed and executed again, pushed and executed again. So now it's time to execute the same select symbol 1,024 times. And that's what it's over. So I think also the developers agree that this should really work, but it should not work without the translate. It's just that the ranking functions basically should work. And as I said, if they fix this device, they will actually return rules, and it will not really result set. So if you put something worse, it's very bad. The next thing I found is one thing that actually works, but it's a bit clumsy. You can use a selectable stop block as a child select. So you select your total data, and then union all, and do a select by stop procedure. Because in that stop procedure, you will for select group, which has a defined order by it, and you will always return the child in that order. So that's a workaround. But it's pretty accessible because we're using all the advantages that you have from the dynamic recursive CTEs. The comments of this, whenever you have to change your CTE on the client side, you will also have to change the recursive store code, but it really does work. So there are all the other problems of recursive store codes. And it's really not it just happens to work. The next option, and one that you actually find really also for other databases, that's that happens first line. A lot of the times for SQL and MySQL, and all of them basically the same trick. And that is the CTE construct the sort path, which works kind of okay with characters. It's not so good with regular data. And it doesn't use any lineage. And it also results after the recursive CTE is executed. And you don't run log with it until the log reads. It's also not some of the very elegant. But So basically, in computation, Firebird 2.5 and 3.0 is the only option you have. Let's take a look. Oh, so, first this one. This is still the same basic example. Just that I put in some more fields. And maybe I can just show you the results. Good. I think the SQL window doesn't like the recursive CTE still hanging around there. Just open up a new one. Okay, that works. So what you're basically doing is you're adding together or concatenating all the results in the order that you want them, and that gives you a nice sorted path. And you can just, in the lower select from your tree and do an order by this constructed path. And this will actually return the child data always in the same manner. It's pretty easy here because this is alphabetical data and you can put it together with slashes. But if you want to order it by, let's say, file size, then it gets a bit more complicated. Prepare another example for that. And this is pretty ugly, really. What I've done here basically is that in every child, I count the child records that are smaller than the child I'm standing on and transform that into a counter. And what this gives you is this kind of sort path. So every child, this is the second child, so it finds one child record that is smaller than itself, so it will return here. And this actually wasn't all kind of data. It uses timestamps, numerical data, whatever. But it's pretty good in components because if you have a lot of childs on the same level, like you have 10 childs, then you have 10 counts which will count through all your child records. So if you look at the statistics here, it's doing a lot of reads. This is not the statistics of that select, I think. I guess that's the output of the previous one. Oh yeah, okay. It's a very small trees, and I only have two child nodes on the same level, so the impact is not that big. But you can imagine if you have a lot of child records on the same level, and you do this counting for every child, then it's pretty bad. But as I said, this is the only reliable way you currently have to do child ordering. So, session time is really over. Let me just give you another 2 or 3 minutes so we can look at this really. What does all of this have to do with cake? Let's take a look at this. We have a cake mixture here with chocolate, and we have one with vanilla. And here in this cake, you know that this is actually the same stuff. It's all the same recipe, just once you have chocolate, it's vanilla. And then you have the icing on top, which is the same recipe. It's also the recipe itself. Now, very common questioning if you manufacture and sell this cake. You can look at the small print here, and it always says how much sugar is in this product, for example, or how much of most stuff is in it. And you have to declare that by law. So, when you have a product recipe like this, you want to find out how much sugar is in that cake. And this is a perfect example for recursive CTE, actually. Let me just close this one, and we'll take that one. Oh, there you go. What I've done here is I have actually 3 tables. One has standing data for raw materials, one has the index information for recipes, and one is the link table that just connects the recipes and raw materials. And you can have recipes inside recipes. I'm afraid we don't have time to do it in detail, but I can just show you the output. Maybe I should just make this. So you can see here that I have the F formulation, then you have the chocolate cake mix, which consists of a basic cake mixture, which again consists of some raw materials. And here I've made a little table of content index, which is also just calculates during the execution of the recursive CTEs, so you can have a nice ordering. And you can see that those 4 belong together. And the chocolate flavor is just as basic cake mixture. Next is the vanilla. And you see that this actually has the same sub-recipe. It's the same basic cake mixture. So this is the same tree, like this one, but they're just linked together in the link table. And we have different flavor in there. One thing you can do quite easily here is this percentage is actually what the recipes is. So it says that this one has 30% of that, 20% of that, 10, 40 of that. And in the recursive CTE, there's a simple calculation behind it, which will give you the level percentage. The screen resolution is really not fun. Anyway, the examples are all in the sample index. If you want to play around with it, just tell me what I can send it to you. It's basically just a calculation of what does the percentage of the main recipe have multiplied by your percentage. And so you can get back what percentage does this ingredient have on the entire cake. So this is kind of nice. You get the entire recipe resolved recursively back. And next thing you can do here is put the same basics on it. You can do a sum of the percentages limited to the sugar, and so this recursive CTE will just return the raw material in the entire recipe. Another thing, and this is I think the last one I can show you because I'm really over the time. Is maybe this one. This is just a list of ingredients. And this is what I mentioned earlier, that you can chain those CTEs. So we have this one recursive CTE here on top. And I have another CTE, which just takes the results of the recursive CTE and groups it and condenses it. And what you get as an output is the list of ingredients. And so you see here for this cake, you need 28.8% of milk. And if you want to make a 5 kilogram cake, then you will take 1.1 kilograms. And so all this calculation is done just on those 2 CTEs that are chained together. Okay, I think I'll have to quit here. So, thanks for your attention. Do you have any questions? No questions? Okay, then I have one last question to you. Want some cake? Come here. Thanks.